Welcome to the week 6 of our Calculus 2 course. Last week we worked with infinite sequences. This is an order list of the numbers, and our goal was to determine whether a given sequence converges or diverges. Some of the basic series we know from middle school. For example, arithmetic series. Arithmetic series is a sum of the sequence in which each following number is equal to previous number plus some fixed constant d. The beauty of arithmetic series is that we can easily calculate a partial sum as n, a sum of first n terms in the infinite series. Let's take a look at the example of arithmetic series. 4 plus 11 over 3 plus 10 over 3 plus 3 and so on. Let's see how to write out general formula for this arithmetic series. In arithmetic series, the first term is going to be called a. The following term is different from the previous term by a constant d. Let's find the difference of the second and the first term to calculate the constant d. As we can see, 11 over 3 minus 4 is equal to exactly negative 1/3. If we'll check the difference between the second and the third term in the sum, it should be equal to exactly the same value, negative 1/3. And indeed, if we'll take 11 over 3 and subtract 1/3 from it, we'll get exactly 10 over 3. This difference continues throughout the entire infinite arithmetic series. 10 over 3 minus 1/3 is equal to 9 over 3, which of course is equal to 3. Since we now calculated constant d, and we know that the first term in the arithmetic series is equal to 4, we also know a. Let's set a equals to 4 and d equals to minus 1/3, and write down our arithmetic series as sum, where index I changes from 1 to infinity, of a constant a equals to 4, plus the index I minus 1 multiplied by a constant d, negative 1/3. The other familiar type of series is geometric series. Geometric series is the sum of terms where each next term in the sum is a constant multiple of a previous term. If the initial term in the geometric series is a, the next term would be a product of a and that constant multiple r. Following term would be a product of ar by r, which creates ar squared, and so on. We also know that the partial sum can be calculated for the geometric series using the formula a times 1 minus r to the n divided by 1 minus r, provided that r is not equal to 1, or it's equal to a times n if r is equal to 1. This knowledge of partial sums will allow us to not only determine if given series diverges or converges, but if series converges, we'll be able to calculate exactly what series converges to by taking limit of a partial sum as n goes to infinity. Let's take a look at the example of a geometric series. 3 minus 4 plus 16 over 3 minus 64 over 9. In order for us to write this geometric series as the sum where index starts from 0 to infinity, constant a times constant r raised to the power of n, we need to determine what our a and r are equal to. Since the initial term in the geometric series is equal to a, let's set a equals to 3. The ratio of the following term to a current term gives us exactly what r is equal to. If ar is equal to minus 4 and a is equal to 3, then r is equal to minus 4 over 3. Therefore, the formula for this geometric series is sum as n changes from 0 to infinity, a, which is 3, multiplied by r minus 4 over 3 raised to the power of n. This is very valuable skill to be able to recognize geometric series when you see one, so let's practice doing exactly that. Write given infinite series as a geometric series in form sum, where index n changes from 0 to infinity, of constant a multiplied by constant r raised to the power of n. Let's say we have the series 10 minus 2 plus 0.4 minus 0.08. Since we've been told that this is geometric series and we would like our index start from 0, let's set the very first term in this sum equal to a. Then our r is equal to the ratio of the following terms. AR to a minus 2 over 10 is the same thing as minus 1 over 5. We can confirm that the ratio of AR squared to AR, the following two terms, is also equal to the same constant r, because 0.4 divided by minus 2 is the same thing as 4/10 divided by negative 2, or minus 4 over 20, which is also equal to minus 1 over 5. Since we know a and r, we can now write this geometric series as a sum, as n starts from 0 to infinity, of a times r raised to a power n. 10 times minus 1/5 raised to the power n. More often than not, we see geometric series written as some sort of a sum, not necessarily starting from index 0 and not really looking like a constant a times r raised to the power of n. So let's see how we can manipulate a given expression for the case term so that we can recognize a geometric series in the form sum as n starts from 0 to infinity, a r to the n. Using the properties of the exponents, we can rewrite square root of 2 raised to the power minus k as 1 over square root of 2 raised to the power of k. Since 1 to the power of k is the same thing as 1, we can rewrite 1 over square root of 2 to the power of k as a fraction, 1 divided by square root of 2 raised to the power of k. This is almost the expression that we want. The only difference is we don't have the index starting from 0. Our index starts from 2. So how do we re-index series so that we end up with the sum where index starts from 0 and not from 2? Since our index k is equal to 2 for the very first term in the sum, we can set n equals to k minus 2. That's the moment where we re-index in the sum. When k is equal to 2, our expression would have n equal to 0. If we solve for k, we'll find out that k is the same thing as n plus 2. Now, let's replace k with the index n. If instead of k we'll write n plus 2, then our index n starts from 0 to infinity, and 1 divided by square root of 2 would be raised to the power n plus 2. Using properties of exponents, we can write 1 over square root of 2 raised to the power n plus 2 as 1 divided by square root of 2 squared times 1 divided by square root of 2 raised to the power of n. Let's simplify things a little bit, because 1 divided by square root of 2 squared is nothing else but 1/2. We achieved our goal. Our expression is written as a sum that starts from 0 to infinity of a constant a multiplied by r raised to the power of n. Our a is equal to 1/2, and our r is equal to 1 divided by square root of 2. Manipulation of the given expression and re-indexing is very often done in order for us to be able to express things as a geometric sum, to be able to calculate exactly what the geometric sum converges to if it converges. So let's work on one more example. Let's say we have a sum where k starts from 1 to infinity. Of a fraction, numerator is 3 to the k plus 1, and denominator is minus 2 raised to the power of k. Let's rewrite this geometric series as the sum where index starts from 0, goes to infinity, of constant a times constant r raised to the power of n. Since our index starts at k equals 1, we know that n equals 0 when k is equal to 1, so n must be equal to k minus 1. Let's solve for k in order to replace the k with the expression in terms of n. Here k is equal to n plus 1. So 3 to the k plus 1 can be rewritten as 3 to the n plus 1 plus 1, and minus 2 to the k is equal to minus 2 to the n plus 1. In other words, we have a fraction where in numerator 3 is raised to the n plus 2, and denominator is minus 2 raised to the power n plus 1. Using properties of exponents, we can rewrite numerator as 3 squared multiplied by 3 to the n, and denominator as negative 2 multiplied by negative 2 to the n. So let's group together 3 raised to the power of n in the numerator and minus 2 raised to the power of n in denominator. This creates minus 3 all the way to raised to the power of n. Therefore, our constant a is equal to minus 9 over 2. This week in the lectures, we will see mixture of different series. We'll try to determine which series is a geometric series. We'll rewrite it in the form a times r to the n as n changes from 0 to infinity, and then we will figure out whether given series converges or diverges. I hope you found those examples useful. Until next time.